Overall performance was pretty decent. Average is 42 out of 60, which is on the higher side compared to what I typically expect in midterms. And so, all right, Peter. And don't worry too much if your scores are lower than average. I think in the end, we still have the final, we still have the project, and we'll talk about both in a second. Amy? Veronica? Chris Conner? Aaron? Right here. Elena? Jonathan? David? Charles? Aslan? Siggy? Grant? Rachel? Bourgeois? So I think I tend to be liberal with things, but if you have any questions, you can just ask me. So in the take-home version, I realized I have to solve myself the Newman part, so it was going to take more time than I had left today. So I was hoping to show you at least a few examples, sketches, schematics, and movies on surface tension. So before I actually start on that, I think for project, we don't have enough time to have in-class presentations, which is ideally what I would have liked, so that you can see sort of a broad range of topics, mostly from fluid mechanics, that you guys can start reading papers and since I don't know how many of you have done research before, and if you haven't, what you'll find is every time you pick a new paper, it's going to be hard to digest everything in the first reading. So you always have to read more than once. And then there are few things that you can sort of get the gist. So the gist is something that you should be able to see also from the abstract what the authors actually try to summarize as the main findings. Then in introduction, they'll try to give you at least hints of where you can find additional information. And then comes the main paper. So what I want is two things. I think we'll do sort of a review. So whenever you'll submit papers, people will give you feedback, and that feedback is usually going to be few pages. You can make it as detailed as you want, but I would expect that it includes, and I'll write this in an email, it includes a significance statement, and the example of significance statement you can find in any of the PNAS papers. And if you already have a PNAS paper, then you should try to make sure that if I assign you a PNAS paper, don't copy paste the significance statement. So I want you to include a significance statement, and then it has to mainly critique that at least summarizes key findings, and then questionable hypothesis. Then there is I think usually I include it as part of the assignment, but here I'll make it heroic effort part. And that is, you create a problem based on whatever is in the paper. Right? So you create a problem and a solution. And then the last part, which I hope we'll be able to share with everyone, is even though we won't have in-class presentations, what I'll ask you to do is make, and again, to give it some format. So if you go to APS, Division of Fluid Dynamics, that conference is being held this week. You usually have 10 minutes to present something. So 10 minutes means most people have anywhere between 6 to 10 slides. And I think most of the things that I've picked for you guys might have movies as well. So try to embed those movies in some way that when we place all these presentations on the Canvas site, each one of you can open and see what other people looked at. So this will essentially allow, even if you don't read the paper from other students in the class, this will at least give you some glimpse of what they were reading and what they were looking at. Yeah, so if we had more time, I would have had this as a homework problem and this as an in-class presentation where usually I ask your peers to evaluate you in addition to. And so that's sort of the gist of the project. For the final, I think I can just take a vote right away. Do you want a cheat sheet? How many want a cheat sheet?
Are we going to be penalized for a cheat
it's gonna
sheet?
be hard.
That's the question.
It's gonna be hard.
It means there's a law of conservation of misery. So you win some, you lose some. If you make it open book, then you have to change some things. If you make a cheat sheet, you have to change some things. I don't think everyone has a textbook, so I wouldn't make it open book. You can make it with cheat sheet, without cheat sheet. You shouldn't worry too much. I think you guys did pretty well for.
I'd like a one cheat sheet, like 1 page double-sided.
Yeah.
I'd look for that. How about you guys?
No.
No?
Okay. So no cheat sheet. You
Aaron,
will have,
I'm with you on that one. I
Okay,
got you.
Thank you.
but you will have all the tables that you would need. So all the conservation equations, all the tables for say.
Can we have them from BSL and from Dean and not BSL?
Okay, I need to work harder for that. Yes.
Because the notation they use is slightly.
The sign is also different. All right, so we'll have no cheat sheet, but we'll have most of the at least conservation equations. Plus, I will include the appendix C from BSL, which is a list of like common differential equations, and then these will be included from here. And also the stream functions and the equations for surface geometry, which we will discuss today and next time. All right, so and then the other thing is final would be maybe around 25% for heat, mass, that includes charge, and most of it is going to be fluids. Yes.
Do you know how long the exam is? Is it a 2-hour exam, an hour and a half, or?
I don't remember, I saw the schedule, but whatever is on the books. So I think it's on a Tuesday, but you can check that. All right, so that's what is left for the semester in terms of what you need to do and what you might be evaluated with. What I hope to finish in next 3 lectures. So in summary, what we are doing in fluids is a set of problems that we did drag flows and pressure driven flows. these are important because most of the time we are transporting things through pipes, and you need to design chemical plants where you want to understand how much pressure you need, how much flow rate you can get. And if you go to industry, like last week when I visited Halliburton, they said every problem that you want to solve, whether it's fluid mechanics, thermodynamics, you will get to work on it as long as you can translate it into how many extra barrels of oil you'll produce per day. Okay? So when you go to industry, you can sometimes get to work on very fundamental problems as long as you can convince your manager that it's going to increase productivity and reduce costs. Drag flows and pressure-driven flows are also used for measuring viscosity, and then once you measure viscosity, especially for non-Newtonian fluids, because viscosity itself is a function of deformation rate, that allows you to have better control and understanding of processing conditions. So those two come handy there too. So we did, you've done problems where you've looked at cone and plate, fluid geometry, and so on. So that's one set. These were all more or less one-dimensional flows. Then we've looked at creeping flows. And in creeping flows, we mainly looked at two examples, and you'll have some homework problems. Both of them involve Stokes' equation, and we also had some discussion of Stokes' drag. So that's very important in context of low Reynolds number hydrodynamics, and in this context, you also learn how to solve for 2D flows, both planar and axis-symmetric. And we'll see an example or two more where the stream function formulation is used. So what is left now is we want to have lubrication, which is nearly one dimension. So it's halfway between 2D and 1D flows. Then we want to look at the high Reynolds number, one example, because this is our boundary layer theory. And then today's goal is to include surface tension. So far we have neglected surface tension, but whenever you have curved surfaces, or if you have surface tension gradients, these can drive flow, and many of your projects involve either lubrication flows or surface tension driven flows. So that will allow you to see at least some more examples. And I am quite biased towards these two. Unfortunately, I don't know why I always push up to the end of the semester, but that's what I spend most of my time thinking about. So surface tension, I'm pretty sure you have at least some familiarity with what surface tension is. What comes to your mind when you think of surface tension?
Interfacial energy.
Okay, that's a good place to start. So if we think in terms of interfacial energy, what turns out to be the case is, if I look at any fluid, and if I look at the molecular picture of a fluid, as long as you have molecules within the bulk, they are surrounded by similar molecules on all directions. And so compared to that, if you are a molecule at an interface, as soon as you come to an interface, you lose out on all these interactions on the other side. So it costs energy to form an interface, and you can estimate that energy to be proportional to total number of sort of interactions you have to get rid of, right? So that, if you think in terms of interfacial energy, then you can rationalize that you can have interfacial energy per unit area, both for liquids and for solids. And for solids to create a surface, you need a certain amount of energy. And then if we go through this definition, where we think of surface tension as free energy per unit area, that allows you to get the thermodynamic definition of surface tension. And in the sense of, so you can use Helmholtz free energy or Gibbs free energy, and that just changes whether you have V or P here. So I suppose most of you are taking thermodynamics or have had some thermodynamics before. And if you've had thermodynamics before, what you might recall is the free energy is, if you write just the differential free energy, then that's sort of related to SdT, PdV, chemical potential dNi, right? So just like chemical potential represents a change in energy for adding a molecule, pressure determines free energy for changing volume, and entropy comes from the dT term. So likewise, you have this extra contribution that is correlated with energy required to increase the surface area. So that's the thermodynamic definition. Then there's a mechanical definition. And the mechanical definition, again, if I write this down as energy per unit area, you can see energy is force times displacement, and area can be written as some length into displacement. So force per unit length has the same units as energy per unit area, and so this is joules per meter square, this is Newton per meter, and both units are used for describing surface tension. So one of the movies that I was going to show you was, if I take a soap film, and you can do this experiment with, so if I take a metal frame and I have a movable frame attached to it, and I dip this into solution and bring it out. So if I bring it out, you will get soap film. And those soap films are usually, when they're thicker than 100 nanometers, you'll see beautiful interference colors. So if you start out, you'll have soap film on both sides. And then you can figure out that there's a force that always acts on this force per unit length. If you then burst the soap film on one side, this actually moves back rather quickly. So that is an experiment that can be easily done. Or the other experiment is where you take a frame and then take a string. And if you take a string, you can, as soon as you let go of the string, it will go and try to make a circular arc here. And so if we think in terms of forces, then the work done in extending movable membrane is by delta x is going to be surface tension or surface energy multiplied with L dx, where this could be a dx. And so force into displacement should be equal to this work done, and that gives you sort of the definition of surface tension, which tells you that this is just force per unit length. And if you go back to the molecular picture, the reason why surface tension arises in the first place is that these molecules want to get away from a surface, so that effectively creates some kind of tension at the surface. And this force per unit length is real. You can do what Agnes Focals did in 1880s. She was she couldn't go to university back then. There were very few universities that admitted women, and she would go and read everything her brother would bring home, and she used to take care of her parents and spent a fair amount of time in the kitchen. And there she developed sort of the early version of a languator. So what she figured out was that this force per unit length, you can measure by sort of creating a pulley and then adding a weight. And she did these experiments with a lot of care and clarity. So she was able to determine that you have to have very pure samples to get the right surface tension, and learned about impurities and learned about how when you add things to water, it reduces the surface tension. And then she wrote a letter to Lord Rayleigh, and he translated it and published it in Nature. And so it's a beautiful story. And then her work was lost for 30, 40 years, and eventually she was given an honorary PhD. And anyway, so this particular method of measuring the actual force on, it could be a ring or a plate. So when it's a ring, it's called a Dunoyer ring. When it's a plate, it's called a Wilhelmy plate. And many labs, especially labs that work with lipids, have some version of a trough with either the Dunoyer ring or Wilhelmy plate, which allows you to measure this force. And this force is something that when I give demonstrations to school kids, and some of the images or movies I had show this, you can actually balance a metallic needle on surface of water because of the overall forces exerted by surface tension. And that's, again, useful information, which is how water striders or small insects are able to balance themselves on a surface of water. And there's a beautiful study from David Hu and Bush on how water striders glide on liquid surfaces. So this surface tension, because it really depends on the interactions between molecules, is a very high value of around 72 millinewton per meter for water. So water has a fairly high surface tension, whereas many of the organic solvents, ethanol, all these tend to have something in range of 20 to 30 millinewton per meter. So, okay, so that's a mechanical consequence. Now, if you think in terms of free energy, if I create a fluid volume, so for a discrete volume of fluid, the overall free energy is going to be minimized if the surface area is minimized. And the minimal surface area allows you to actually solve lots of problems using soap films. Like if you have to find the minimum distance between 5 different points on map, you could just put 5 pegs there and then create soap films, and they would actually give you the minimum path length. So I'll post some videos. Some of them are meant for, they can be watched by even high school kids. So those are just things you can watch on your Thanksgiving break. But the minimal surface area in the case of discrete volume of fluids gives you sort of a spherical shape. So that's why really small drops are spherical. Now, if I take a drop and I hang it from a nozzle, so this geometry or this configuration is called pendant drop. So in this case, there are two forces that act on it. So the two forces are gravitational force and then capillarity or surface tension force. So capillarity or surface tension force wants to minimize the surface area, so tries to turn into a sphere, whereas gravity pulls on it. And so for a given volume, you get a particular shape that depends on surface tension. And this idea is a very powerful idea because that's used in pendant drop tensiometry for measuring surface tension. So you can write the code yourself and do this analysis. But the key thing to know is this pendant drop, there's a certain amount of time that's needed for making a pendant drop. So for measuring absolute surface tension, it's fine. But then there is something else that we often worry about, and that is if you have impurities, if you have mixtures, then that can reduce surface tension. So that's one thing. The other thing that we intentionally use to reduce surface tension is class of molecules that are known as surfactants. So this includes soaps, detergents, lipids, and surfactants just means surface active agents. So that's the short form for surface active agents. So whenever you add something like a soap, so soaps are derived from natural sources. Detergents are similar things but made in the lab. The structure of a soap typically is, it's like a Janus particle, or it's an MP file. So what you have is a hydrophilic head group and a hydrophobic tail. And because it has a hydrophobic tail, when you add soap to liquids, the energetically favored configuration for these soap molecules is to try to get to the liquid-air interface. So once they get to the liquid-air interface, they can populate the interface in such a way that all the hydrophobic regions are pointing towards air. And so what you're doing is you're replacing molecules of water by something that's similar to organic solvents. So that reduces the surface tension. And in real processes, this happens over a period of time. So if I start with a clean interface, then the surfactant will undergo mass transfer to the interface over a period of time. And if you were measuring, say, shape of the pendant drop, the shape of the pendant drop will evolve over a certain period of time. For small molecule surfactants, the evolution takes place in like 100 milliseconds. That's actually even shorter than the time needed for making a pendant drop. But if you look at things like proteins or polyelectrolytes, they take a fairly long time. So So, like we are doing experiments right now where we try to use polyelectrolytes and it takes 5-6 hours, and even then you don't reach the equilibrium value. But that mass transfer process, again, we are not going to do any problems in class anymore on this, but I will upload a paper or two that discuss how the mass transfer of those surfactants to the interface can be solved as a diffusion problem. And if you have charges present, then the mass transfer also needs to include a term for migration. And so everything that we've learned can be used for doing a very detailed analysis of what is known as adsorption kinetics. And some of these analyses have been applied in I think Tyrrell group. They've used some of this analysis, and also Mohan's group, I think. All right, so that's sort of the one set of things about surface tension. And whenever we are trying to make drops, bubbles, foams, emulsions, or if you think about jetting, printing, coding, all these scenarios involve free surface flows, which means you always have, in most of these cases, you have a fluid-fluid interface. The most generic thing would be the fluid-fluid interface. In some cases, it's going to be liquid-liquid. In other cases, and so whenever I have two fluids, A and B, then we usually use the term interfacial tension. So for two liquids, we use interfacial tension. When it's liquid and a gas, we typically use surface tension, but they are the same thing. So there's a whole range of applications that involve free surface flows, and in those free surface flows, in the boundary condition, you have to consider the effect of surface tension. So now the next question is, how do we account for that? But before that, I'll also say two more things. So one of them is Laplace pressure, and we'll derive this in few minutes, but from the boundary condition, but you can also look at an alternate derivation of what Laplace pressure is. So if you consider a bubble in a fluid, it will have a particular value of surface energy. That sort of depends on two things. Of course, the interfacial tension and the area. So the area is going to be 4 pi r squared for a bubble. So that's the surface energy associated with a bubble. Now, if we change in surface energy or total energy on expanding or contracting, the bubble is going to be given by surface tension into a differential area, and so that becomes 8 pi r gr. So this is the change in surface energy on expanding or contracting. So it turns out that whenever you have a curved surface, there's a delta P that exists across a curved surface. So pressure difference exists across a curved surface. So because of this pressure difference, you have to change area or to change this volume, you have to do work which is then related to force times displacement. So force is pressure into area times displacement. So if we equate these two, then you see that there is a pressure difference of 2 times surface tension divided by radius. So if you have a small bubble, it has a high pressure. If you have a large bubble, the pressure difference is smaller. So now if I go and think about a foam consists of lots of bubbles that are separated by thin liquid films. How long these thin liquid films last really depends on how quickly fluid can drain out of them. And in that context, to do the complete analysis of the hydrodynamics, we'll use a lubrication theory that we'll cover next lecture. But in these bubbles, if somehow the drainage occurs and then you have a rupture of the thin film that separates two bubbles, if you have a small bubble and a large bubble, which direction is the fluid flow going to be? Which one has higher pressure?
Small bubble.
Yeah. So the small bubble gets eaten up by the big bubble. Right? So rich get richer. That's sort of the philosophy this foams and emulsions also follow. Yeah.
When you insert napkin into water goes up. Is it because of surface tension?
Yep.
But it doesn't minimize the surface area.
So then the next thing that we also want to examine is, that's a good question, and the next thing we should mention is wetting. So now when I bring a solid and a liquid in contact, and this is something we have to think about, the wetting properties is something we have to think about every day when we're washing dishes to designing any sorts of coatings. The idea is that if I have a particular solid substrate and I place some fluid on it, then there are 3 surface energies that you have to worry about. So what you're doing is you have a solid air surface energy, and as soon as you place liquid, you're replacing it with a liquid air interaction and a liquid solid interaction. So whether something spreads or not on a surface more or less is determined by balance of these surface energy per unit area. And so this pressure is called Laplace pressure. So Laplace and Young were actively thinking about surface tension effects in sort of the early 19th century, 1805 or so. What Young pointed out is that for a given choice of liquid and a solid, you will end up with a particular value of contact angle. So this angle is called contact angle. And that contact angle has to, if we do the force balance, so if you do the force balance, then that force balance leads to cos theta, which is going to be a particular value. Now if you go and look at the discussion in Dean, there's maybe a page of 2 of discussion on everything that we try to write down here. And so if you want to figure out whether something is going to spread or not, you have to calculate so-called spreading coefficient. The book that is really good for this is called capillarity and wetting phenomena, and I think I'll post maybe a chapter from it, so that if you're interested, you can see some of the other. That's from Pierre Dijon, Rochard, and David Kelly. So wetting really depends on surface tension of the fluid. And if I think about most of the times when you cook, you use oil, right? So you use oil, or most of the food material as some organic matter. And because it's organic matter, the interaction with water, which is used for cleaning the oil, is not favorable. So one easy way to make it more favorable is to reduce the surface tension of your cleaning solution. And that's where soap comes in handy. There's another reason why you use soap, and that is because when you have lots of surfactant in the solution, or lots of detergent in solution, it spontaneously self-assembles into these supramolecular structures, which could be spherical, which could be cylindrical. They're called micelles. So within the liquid, when you add too much soap, you have lots of these micelles, and by doing this, they are able to have the hydrophobic part inside and hydrophilic head outside. So as soon as a micelle comes in contact with some oil that's stuck to your clothing or to your dishes, that oil then goes and hides inside and is carried away. So that's how most of the detergents and soaps work. And bile salts in our stomach do something similar with fat. So they are able to take fat, and the digestion involves this. If you end up working with Juan or Stuart or Matt, you probably will be thinking a lot about hydrophobicity, self-assembly, and some version of micelles that is used also for drug delivery, among other things. So there's a lot of thermodynamics that is involved in trying to calculate how many of these molecules would be there, and under what conditions you get micelles to form, and then if you, instead of having a small hydrophobic head and a tail that is like 12 to 20 carbon long, which is what surfactants are, you could consider other systems where you have a polymer that loves water and a polymer that hates water. And if you have covalent bonds between them, they are called block copolymers. And those block copolymers also self-assemble. And again, a lot of work is done in UChicago as well on understanding this. All right, so far what we've said is that whenever there are surfaces, you have to think about surface energy per unit area. That surface energy per unit area creates a force per unit length. That force is measurable using either denoising or Villamy plate. That force also depends on the choice of the fluid, because interactions of the fluid really determine what that value is. The value for organic solvents is much lower than for water, and they are compounds like surfactants, soaps, detergents, lipids. In fact, proteins are also somewhat similar in the sense that they have hydrophobic and hydrophilic parts. So they also like to go to interface. But proteins are somewhat bigger than soaps or detergents, so everything happens at a slow rate. So these things, when they go to an interface, they also help in stabilizing things like foams and emulsions. And if you think about coffee foam, then there's a fair bit of protein that comes from milk, but there are also coffee particles that can go into that foam and stabilize it. And then the other thing we said was, whenever there is more than one force present, then the actual shape of drop really depends on interplay of those forces. So this is a static example. We could have example where you can create a shear or an extensional flow. And in shear or an extensional flow, you can deform these drops. And the deformation of drops now is going to be a competition between how much stress you're applying due to flow and then capillarity. And something like this is also used on a daily basis. What unfortunately we won't get any time to discuss is things like jetting, in which case you start with a cylindrical fluid element, and in this cylindrical fluid element, if you create thickness perturbations, then those thickness perturbations eventually can grow for some range of wave numbers or wavelengths, and they can grow, and they usually grow, and that leads to eventually formation of problems. So this is a very nice perturbation problem, but I don't think we'll have time for this. And understanding interplay of capillarity, viscosity, or viscous stresses, inertial stresses, is something that allows you to design all sorts of inkjet printers and spray guns and so on. And so that's again something that I spent a fair bit of time looking at in UChicago, Sid Nagel's group, and then Henrik Jaeger have done, and Wendy Zhang have done a lot of work. Similar interplay also occurs every time you have sort of a dripping. So every time you see dripping, there's similar interplay. There's a lot of interfacial phenomena that goes on in daily life. Every time I drink beer, it's, I don't know, for me it's too many phenomena to notice. But if you don't know those phenomena, you can drink and use. I can't anymore. So, all right, so now what we want to do is, this is sort of a background on what happens when there are interfaces present and when surface tension is relevant. Now let's look at the effect of surface tension on the boundary condition at a fluid-fluid interface. So that's sort of the key in terms of solving any of the fluid mechanics problems where free surfaces are involved. And again, you might start in one field now, and you might pick a PhD thesis that falls under a particular area where you may or may not use some of these ideas, but over time, over 20, 30-year time frame, I'm sure many of you will return to some of these problems. So, like, I find this fascinating that if you go back and look at Matt Tyrrell's advisors, papers, and books, it's all fluid mechanics. So he went from there to now you hardly see him even go to fluid mechanics conferences, right? So that can happen over the course of a rich career. All right, so now we want to get to stress balance. And this is stress balance with surface tension. And the key thing is we again go and draw the same interface that we had drawn before between fluid 2 and fluid 1. And we again draw control volume. Now, if I have an interface and I draw a control volume, then this control volume is going to intersect the surface. So there's a control volume of thickness 2L, and this intersects over this contour, and due to surface tension there is a force that acts tangentially on the surface. So there's an extra force that is arising tangentially on a surface, and this contour is where you have intersection of the volume, control volume with the interface. Sorry. So if we now write the conservation of momentum exactly like we had written down before, we just need an extra term for surface tension to be added. So we had written this using the Reynolds transport theorem in the first lecture on fluid mechanics. And we said the rate of change of momentum is given by body forces plus surface forces, which were buried in this stress vector, and then we have one extra term which involves a contour integral. And in the first lecture, then we had moved terms around, taken the limit of v goes to 0, and so if you recall derivation for stress equilibrium, we'll do the same steps. These two terms drop out, this term remains, and it becomes S of n in 2 minus S of n in 1 ds. So we had used this is equal to 0 earlier, but now we'll have an extra term. So because of this extra term, which arises due to surface tension. Right, so there's an extra term that arises due to surface tension, and we can this contour integral can be converted into a surface integral. So again, even though the mathematics might look different, the strategy is always the same. The strategy is we try to have everything converted either into dV integrals or ds integrals so that we can get a differential version of this. So our goal is to get a differential version of stress balance that includes the surface tension term. Because once we have the differential balance, then we can write the boundary conditions and we can go on to solve problems. So here, this we are just going to write the final result as it emerges from a derivation given partially in the appendix A5, I think. So it ends up giving you two terms, and those two terms are the terms that play an important role in terms of dictating how surface tension affects flows. So the first one is a surface gradient. And the second one, this edge is called mean curvature. So before we discuss these, let's write down the differential stress balance. So now, across an interface, you end up with two extra terms. And this can be rewritten as two boundary conditions. One in the normal direction, normal to the interface. So there you have tau n in 2 minus tau n in 1 plus 2 h gamma is equal to 0. And the other one is tau nt 2 minus tau nt 1 is equal to, so we are now taking we take the normal component and then we take the tangential component. So for normal component you take dot product with n, and for tangential we'll take dot product with the tangent vector. So now let's think about these two relationships. The first thing you find is if you have no flow, then this tau term, which is your deviatoric stress term or viscous term, goes away, right? So whenever there is no flow, the tau term is absent. But whenever there is no flow, if there is any curvature, then you'll have a pressure difference. So this is the static case. So in static case, you always get a pressure difference. Now if you consider case of a bubble, then it turns out that you have P1 minus P2 is equal to minus 2 H gamma. And we'll write down the full expression for curvature in few minutes. But for sphere, it's supposed to be minus 1 over R. And so that gives you delta P as 2 gamma over R, which is the Laplace pressure for a bubble. But the point is, even if there is no flow, you are always going to have a pressure drop as long as there is a curved surface. Now if you look at the second term, what this implies is, if there is ever a gradient in surface tension, that is going to cause flow. Now this gradient in surface tension, there are many examples that I can think of. One of them is the example of something that now I have a student doing experiments on, and I got to present in AICHE on this, which was kind of fun because lots of people came in to see tears of wine. How many of you know what tears of wine are? How many of you drink wine or have friends who drink wine? So here's an experiment you can do over the Thanksgiving break. So the experiment involves, you can compare between rum, limoncello, wine, whatever. So if you pour any of these sort of high concentration, so it has to have high enough ethanol concentration into a glass. Then because of how this meniscus is, in this region, the evaporation is, so there's a little bit of film that climbs up because of surface tension, because of that wetting. But in this region, the evaporation of ethanol is faster. And so as ethanol evaporates out, the concentration of water goes up locally, and water surface tension is higher, so it's able to pull more fluid up. So this drives flow of a fluid up to a certain height, and if you drink rum or brandy, then you'll see the height is typically higher than a strong wine. And then eventually it gets to a certain height and then starts to roll back. So when it rolls back, it has a shape of a tear, so those are called tears of wine. Right, so the talk that I gave was trying to look at some fluid mechanics aspects of it. But the fun part for me was the last slide had comparison between experiments with wine, limoncello, brandy, rum, and by the end of that, I think the smiles on audience were pretty big. So this is one example of so-called Marangoni flow. So whenever there's a gradient in surface tension that drives flow, it's called a Marangoni flow. And in this case, if it's a mixture of two fluids where one has very high surface tension compared to other, and the low surface tension one is more volatile, then you can get something like this tears of wine formation. The other scenarios in which you can get concentration gradients in surface tension are if I take, say, a fluid droplet, say a droplet of water or water glycerol mixer, or it could be a blood drop, and place it in another fluid which could be immiscible with it, and I shine laser on it, on this fluid. So if you use IR laser that locally heats the fluid, then that causes a temperature gradient. And because surface tension depends on temperature, this can create a surface tension gradient, and then that actually drives a flow. So my first paper is all a study of thermocapillary flows done in this way. These kind of flows then arise whenever you have non-uniform temperatures, sometimes because of evaporation, sometimes because you have contact with a heated surface. And in that case, as soon as you get a concentration gradient or thermal gradient creating a gradient in surface tension, that's going to create a flow. Most of these flows, most of the effects of surface tension become manifest only when you're looking at small objects or small sizes. So as we go towards microfluidics or trying to make smaller and smaller feature sizes for all sorts of microelectronic applications, then in those cases the effect of surface tension gets manifested more and more. When I was a postdoc, there were two grad students who, I think they had a startup. I don't know what happened to that startup, I should check. So their startup was based on this other idea of Marangoni flow. And so if you take so this is a Marangoni flow experiment that can be done in a bathtub. If you take a plastic boat, a leaky boat, and add soap to it. So when you add soap to it and it's a leaky boat, so as the soap leaks out, locally it reduces the surface tension, and that creates a surface tension gradient, and this can drive the boat forward, and you can get very nice motion of a leaky boat. Or other way of doing this experiment is to use camphor. But what these two grad students wanted to do was to have a similar Marangoni flow driven mixing device for martinis. So it seemed to work well, and I think they had picked something that was edible, but I don't know how successful they were in convincing people to have that. So this this term is going to be important whenever there's a concentration gradient. That term is going to be important whenever there is a curvature. Now, the next question is, how do you actually get this curvature term? So it turns out that description of free surface flows is much harder than flows within channels for one reason. And that reason is you have to solve not only for the velocity field or pressure field, but you also need to solve for the shape of the interface. So the shape of the interface becomes, it couples into your fluid mechanics problem. And that makes both simulations and experiments and analysis a little bit harder, because you not only have to follow what's happening in terms of flow field, but you also have to see how the surface itself changes. And so we need a description for surface, and that essentially takes us into the next topic, which is surface geometry considerations. So we need to figure out how to find this surface gradient, and we also need to figure out how to find this curvature. So those are the two things we need to do. And I think we'll run out of time, but I will still get started with this. So if you, again, this is discussed in appendix in D. So if you consider a surface position vector, Rs, that depends on U and V, then vectors tangent to the surface can be defined as A, which is dRs over du, and B, which is derivative of Rs with respect to dV. So those are the two vectors tangent to a surface, and their cross product. So now we have two vectors tangent to a surface. So we take the cross product of two vectors that lie on a surface. The cross product is going to point normal to the surface. And so this is how you define surface normal. Now, if we were looking at a Cartesian coordinate system, in which case u will be x, v is y, and the surface is z, which is a function of x and y, then your Rs can be written as x ex plus y ey plus z ez, but z is f of xy. One minute. All right. So from here we can write tangent vectors. So A is going to be derivative with respect to x. So when you do that, you get 1 ex plus 0 ey plus df over dx ez. And the other tangent vector is b, which is drs dy, so 0 ex 1 ey plus df over dy ez. So using this, we can get unit normal. And for different coordinate systems, the expressions for normals are given in a table in the appendix. And we will provide you those tables in your exams. But if we take the cross product of these two, then that will give us the surface normal, which turns out to be equal to minus df over dx minus df over dy ey plus ez divided by its magnitude, so that is square of first term, square of second term, plus 1. So that's definition for unit normal, and next time we'll discuss how surface gradient can be derived from unit normal, and also how curvature is related to divergence of this normal. So I think you're going to have a course evaluation thing, so we'll continue next time.